Hi, my name's Dr. Nicola George and I recently completed my PhD at the University of Liverpool. And this paper will provide the details of one part of my research, and that is looking at how Romans manufactured their silver coinage. And in particular, I'll be discussing my experiments in Roman minting. I'll be running through the background to the investigation, and then I'll move on to explain my experiments. And then finally, the results and conclusions. Also, I believe we have some questions. My thesis was an investigation of 3rd century Roman silver, and I looked at the period AD 193 to 270. My research addressed the lack of microstructural data for Roman silver coins. Now, in the past, this has impeded our understanding of the methods used in their manufacture. Previous investigations into Roman silver coinage have focused on determining episodes of debasement, and debasement is the lowered value of the silver coinage with the addition of copper. Now, episodes of debasement are identified by determining the fineness and the weights of different issues, but comparatively few studies have actually looked at the methods used to manufacture the coins. Destructive microstructural analysis is actually often necessary to establish the minting technologies employed by ancient moneyers. And since ancient coins are precious objects, they're often subject to strict sampling regulations. So this means a limited access to coins for destructive analysis. And that is actually one of the main reasons for the shortage of microstructural data for Roman silver coins. For this investigation, I was actually really lucky, and I was given the permission to section 36 Roman silver coins. They were all minted between AD 193 and 270, and they were investigated using optical microscopy, scanning electron microscopy, and then complementary elemental data were acquired using energy dispersive spectroscopy and mass plasma atomic emission spectroscopy. Following this investigation, I carried out the experiments to explore two specific aspects of the minting process. Firstly, I looked at the casting process, and then I also looked at the different potential silvering technologies used to disguise the lowered silver content. However, today I'm only going to be discussing the moulds and the casting experiments. The blanks created in the experimental castings, they provided microstructural data acquired under controlled conditions, and then they could be compared to the ancient examples. So prior to the microstructural and experimental investigation, research was completed to understand the current knowledge on Roman silver coin manufacture. What I found was that many aspects of the production process used to create the coins were actually unknown. So this is partly due to the lack of archaeological finds associated with Roman coin production, and most notably there is an absence of flam moulds in the archaeological record. A lack of finds can be explained in a number of ways. Authors have suggested that the intermittent nature of mint operations meant that minting was often done in movable structures, and these mints are difficult to locate. Therefore, the archaeology associated with the Roman mints are also difficult to locate. And another potential explanation is the secrecy exercised at Roman mints. So to prevent counterfeiting, regulations were imposed on mint workers and penalties were given to those removing materials from the mint. So this could indicate that the minting materials were destroyed after use. Due to the lack of minting finds, much of the current evidence that we have comes from the coins themselves. However, as I stated before, there is a preference to select non-destructive analytical techniques to investigate the coins, and this has led to a lack of microstructural data and information. So currently, what do we know? Despite the lack of archaeological evidence, two crucial stages of production were necessary for the creation of the coins. Firstly, the fabrication of a blank or a flan, and secondly, the impression of the obverse and reverse design. This paper will be examining only the former. Now, in the past, the lack of evidence has been used to suggest an invisible form of flan production, such as pouring out onto a flat surface, chiselling from a cast metal rod, which this is usually connected to bronze coins, and then also cutting out the blank from a metal sheet, similar to a cookie cutter style. Looking at evidence from other archaeological contexts actually suggests that flans were cast in moulds, and examples can be found in clay, stone and metal. The lack of moulds may be explained by their destruction after use, and in the case of bronze mould, the mould could be melted down for its metal content. So before sectioning the coins, I completed a visual inspection and I identified that remnants of casting channels called sprues were on some of the coins. Now this indicated that the flans were cast in a mould, and the presence of casting sprues also indicates towards the mould typology, which would have been one with individual depressions, each connected by channels that would distribute the molten metal. Following the visual inspection, I then completed the microstructural investigation, and the evidence from the Roman silver coinage also indicates that the coins were cast. Now, this electron micrograph shown here is of the heart metal of a Roman denarius minted under Septimius Severus. And in the image, you can see copper-rich dendrites, which are dispersed amongst a silver-rich and eutectic matrix. The phases are elongated along the length of the coin, and this is indicative of striking. However, the deformation of the grains is actually minimal, and when you can compare it to silver copper blanks that have been cut from a rod and hammered, then the grain deformation would be much more severe in those examples. So from this microstructural investigation, I could actually rule out some of the methods mentioned before. So following this, experimental work was carried out to gain some information, and these experiments addressed two key issues. So first was the casting process of the blanks. Following the mould survey of moulds from other ancient contexts, 3 potential materials were identified. Now these materials, like I said, included clay, limestone and bronze, and all of these materials were tested in the experiments. And the purpose being was to gain practical information about the casting process and then hopefully gain some relevant insights. The second issue that was addressed was the artificial silvering techniques used to disguise the lowered silver content. However, this paper will only be covering the casting process. The evidence from the visual inspection suggested that ancient silver copper flans were produced in moulds with connecting channels, and the indentations are connected by channels which allow molten metal to flow throughout the mould. Now, when designing the mould, I looked at the average diameter for the coins investigated, and that was around 20 millimetres, and the thickness was 1 millimetre. So to produce blanks of a similar size, standard indentations of 20 millimetres diameter and 3 millimetre depth were made. The depths of the indentations were made larger to account for both shrinkage in the mould and the reduction in size caused by striking. So the mould materials. With the clay mould, to create the clay moulds, a small amount of water and 10% weight sawdust was added to the modern potter's clay, and this was then formed into the correct shape. The addition of sawdust was used to improve the refractory properties of the clay by allowing gases to escape when the molten metal was cast into it. Following the creation of the mould, it was thoroughly dried out at room temperature for several days, and this was just to ensure any excess moisture was removed. For the stone mould, a block of limestone was acquired from the Department of Environmental Science at the University of Liverpool, and I used a small handheld drill to create the indentations and channels, and then the stone mould was then dried in the furnace to remove any excess moisture before casting. The bronze mould was created by the engineering department at the University of Liverpool, and the mould was fabricated from a high tin bronze with 12% tin. And evidence from the mould survey demonstrated that Roman moneyers were using high tin bronzes to fabricate their official dies, and it is possible that they also used this alloy for their flan moulds. So the casting process. The metals used in all the experiments were pure, so the copper came from copper pipe and the silver used was industrial grade silver granules, and experimental blanks with specific alloy compositions were selected to imitate those found in the ancient coins. A clay graphite crucible was used to melt the metals, and before entering the furnace the metal was covered with a thin layer of powdered charcoal to prevent oxidation, and drawing on previous experiments by Ottaway and Wang, charcoal was also used to dress the moulds before casting. Here is just a short video of the casting process. All of the moulds were preheated to 350 degrees in a drying oven, and this was to prevent rapid cooling of the molten metal upon contact with the mould, and that would actually spoil the casting. So the alloys were melted in the furnace at 1250 degrees for 20 minutes and then poured. And then following this, after the flans had cooled, they were removed from the moulds. So moving on to the results. Although capable of producing blanks, the clay mould presented a range of issues. At the drying stage, the two sides of the mould contracted, making it difficult to achieve a close-fitting connection. If both sides of the close-connected mould had not been completely flat, then flashing will occur and the molten metal seeps out. When the molten metal came into contact with the mould, they often fractured. To facilitate the mass production of coinage, moulds must be able to produce large quantities of flans in a single casting, and the introduction of the molten metal into multiple channels would increase the probability of mould failure. Modern potter's clay is similar compositionally to the clay used for ancient refractory items. These experiments suggested that the clay moulds would be used only once and new moulds would be required for each casting. And when you consider the mass production of blanks, this would significantly increase production times. So for this reason, it appears that clay moulds would be an impractical choice when considering the other materials available. Now, the investigation found that the limestone was more than suitable for casting silver copper alloy blanks, and it was actually possible to reuse some cavities in the limestone mould twice or even 3 times before they were no longer viable for casting. And once a suitable stone had been selected, the durability of these moulds would be greatly beneficial to the ancient metallurgist. So it does have obvious advantages of a mould that could take 2 or 3 castings. That would actually reduce the manufacturing time significantly at mints. And finally, the initial bronze mould castings were unsuccessful. However, upon reflection of the experiments, I did question the effectiveness of using powdered charcoal to coat the mould. The powder just didn't adhere to the surface and it didn't provide the necessary lubrication. So as a result, an additional set of experiments were carried out with just the bronze mould, and this time I used a liquid graphite as a release agent on the bronze mould. And the use of the liquid graphite as a coating agent significantly improved the castings. With this just small adaptation to the casting process, it was possible to cast blanks with all of the intended compositions. And one of the striking features of the blanks cast in the bronze mould was the standardization achieved for the size and the weight of each coin. So finally, I sectioned all of my blanks and gained microstructural data for each of them. Now, I found that the grain size observed when all of the blanks produced during the experimental investigation are actually much smaller than those found in the ancient examples, but all of the experimental blanks were left to cool slowly within their individual moulds. But despite this, the grain size is still much smaller. So this evidence could indicate that the ancient blanks were left to cool over much longer periods, or another potential explanation is that ancient monies were casting into moulds that were contained within a furnace structure and then allowed the entire furnace structure to cool after casting. So finally, the conclusions. From the current information, it's not possible to conclusively determine which mould material was being used to cast Roman blanks. However, the bronze mould offered some practical advantages over the other 2 materials. The bronze mould was less susceptible to complete failure compared with the clay, and it can be reused many times. The standardisation also achieved using the bronze mould was quite striking. In addition, any moulds made from bronze would be melted down for the raw materials following use. This is actually a good explanation as to why no Roman flan moulds have been found in the archaeological record. So, at present, these conclusions rest on findings from castings within a relatively small mould, and it would actually be really interesting to see if this success could be recreated when the size of the mould is scaled up for mass production. So that would be a line of inquiry for future research. And that is the end of my presentation. So if anyone has any questions, then you can join me online.